So this is the chapter 28 problems. We went over a number of the chapter 28 conceptual questions in class, and hopefully those made sense. Again, we spent a whole day on those. These only 5 problems. Most of them were even though. Again, I think we went over most of these in class. Problem 1, key thing here is if you're looking at a charge on a proton going through the field, or basically you're trying to figure out the final speed of it. If it's released from rest, the first thing you want to do is find the force. So in a uniform field, that's the rearrangement of E equals F over Q. So we get a force in the proton, which has the same charge magnitude as an electron, of 8 times 10 to the negative 15th newtons. Then we go to Newton's second law, as we so often do, to find acceleration, ridiculously high acceleration. So it's got to be able to accelerate for much less than a second, since the speed of light is the maximum speed in the universe for matter, and that's 3 times 10 to the 8th meters per second. Actually, it's the speed limit for everything. And then finally, we're going to use kinematics equations to find V final. There's a couple ways you could do this. I chose this particular way. The distance across here was 2 millimeters, so 0.002 meters. They gave me a final speed well under the speed of light, 138,000 meters per second. For problem 26, it's saying that at this point, there's a voltage or electric potential of plus 3,140 volts. So therefore, I've got to find the unknown charge at this corner. So I know the potential is the summation of the individual potentials caused by these individual charges. So I can figure the potential caused by this charge, which is 2 centimeters away, plus 5 nanocoulombs, and this charge, which is negative 5 nanocoulombs at 4 centimeters away. Then I can figure out the distance from this point to this unknown charge by using Pythagorean Theorem. That's 0.0447 meters. So this one was the positive charge gave me plus 2250 volts. The negative charge up here gave me negative 1125 volts. So that means I need an additional positive 2015 volts at the unknown charge's location to give me the total potential of plus 3140. So working that back into the KQ over R formula with the R that I found out over here gave me a charge of the unknown of 1 times 10 to the negative 8th coulombs, or plus 10 nanocoulombs. We were given this for problem 28. This has to be a positive charge because it has a positive electric field to the right of this and negative electric field to the left. This has to be a negative charge because it has a positive electric field to the left of it, meaning it's pointing toward the right, toward B, which is characteristic of a negative charge, has a negative electric field on the right side, which means again it's pointing toward B. So the ratio of charges has got to be 1 to 1 to get this type of symmetry. And then this is a graph of the potential versus position. If I have a field pointing to the right here, left here, that doesn't matter. What does matter here is that it's a positive charge, therefore around it would be positive potential. This is a negative charge, so around this would be a negative potential. Problem 35, I think we went over in class. I think it was hard to visualize because you're trying to think about how far above and below this x-axis you would be in order to have 0 volts or 0 potential. The key thing is that the ratio of this distance to this distance has got to equal the ratio of this charge to this charge. So this obviously would cause a negative potential because it's a negative charge. This would cause a positive potential because it's a positive charge. If those ratios are the same, then the voltage would be 0. So I ended up doing this. Has to be plus or minus above or below the x-axis. This one I liked a lot. I could see this, something like this coming up on an AP exam, either multiple choice or something related to part of a free response. This proton has 50,000 meters per second here. It's asking how fast it would be going here. Since the proton, it'll be accelerating toward the negative potential. Therefore, it's losing potential energy, gaining kinetic energy. It doesn't have only potential energy at point A, however, because it's already moving. So therefore, I've got to look at this more general equation. Again, I could think of this as at 0 volts, and this is at plus 40, or I could think of this at 30, this at negative 10. It doesn't particularly matter to me. Mathematically, it'll come out to be the same. So I chose delta V, which is a change in potential, and I chose that as my zero potential location. Came out to about 100,000 meters per second. So hopefully those made sense.